So my poster is about preconditioning. When you just a bit of context, when you do incremental for divars, the classic one, what you do in the inner loop is trying to invert a matrix. So you to solve a linear problem that is A delta x equal B, but with A that depends on x on the nonlinear state. Okay, and this matrix A is generally not well conditioned. So what you want to do is to find a good preconditioning, and actually what you solve as a problem is this HA of x delta x equal HB. The problem is that since A depends on x, you want your preconditioning to change when you change your state. And a good way to, well, you don't have access to the inverse of A, that would be the perfect preconditioning. So what you are looking for is for a cheap approximation of this. And one that is quite good for that is so-called the LMP, limited memory preconditioner family. That basically look like this. So you only need a relatively small set of vectors like eigenvectors of A or Ritz pairs and so on. So that's a small r that you have here. So S is a matrix of these vectors, and you can get a good preconditioning with this formula that is a bit complex. The problem is that it can be quite expensive to get, and in particular because you need to compute this A times S. So if you have, you really cannot do it with a large number of vectors. And the idea that we are looking into is, can we get an approximation of this LMP using machine learning? So trying to get a CNN, a neural network to produce a preconditioning that it depends on the state, and that try to mimic this kind of formula here, because we cannot try to learn the full inverse matrix. So does it work? Well, you can see on the poster. Sure.
Thanks. Yes.
Good morning. I'm Juliana Matranga. I'm a PhD student at University of California, Santa Cruz. I work with Andy, and this is the work I did for my master thesis a couple of years ago, and it's thinning techniques for remote sensing observations in support of ocean data simulation. The motivation for this work is that the increasing number of observations to use in data simulation brings some computational and numerical difficulties. So we wanted to test if thinning observations is still a good idea, and we can have some good results using less observations. I implemented two different algorithms for two very voluminous data sets that we use for a simulation. In this case, I use a simple thinning technique for the HF radar radial velocity observations, in which I combine several neighboring observations into super observations. It's like the mean of those observations. And for gridded satellite data, I implemented an algorithm which detects regions of high variance, and we keep those observations, and we subsample areas with low variance. Here we can visualize these two thinning methods, how they look. And our main finding was that the 4D bar analysis wasn't significantly degraded after thinning. So this gives us the possibility to keep working on this. And the idea is in the near future to test these thinning techniques in a near real-time forecasting system that is running UC Santa Cruz.
Grazie bien.
So this is the poster about sea ice data simulation, which is slightly related to Arctic. I will try to use in Nansen Center, we're developing this ensemble data simulation system for the next generation CIS model. I will present in the next talk about this multi-scale alignment technique, which we use to reduce positional mismatch in the ice features. So first, I apologize for the slightly different name of the poster. I merged the DA part with a little bit with the predictability part because we are also exploring how predictable the CIS is. The second thing I need to apologize is I forgot this poster in my hotel room today. I hope tomorrow I can bring it and you guys get a chance to see it. Thanks.
Yeah. Next poster is Garcia Olivia. Garcia Olivia.
Okay. Hi, everybody. My poster is going to show you some results about an assessment we did using atmospheric constraints against ocean constraints in the for getting seasonal to decadal predictions. So I'm going to show you the results. Overall, what we did was to compare whether it is important or not to use full field or anomaly initialization from the atmosphere to initialize the ocean, and also whether if it was useful or not to constrain only the momentum, for example, or also to include temperature of the atmosphere to initialize it. So I'm going to show you all those results. Overall, what we found was that anomaly or full field initialization will be good for some in some cases and in some regions, and for some timescales. Okay, so yeah, I think that's more or less everything. If you have some questions, or if you are what's the word? Curious about it, you can visit me, the poster number 4. Okay.
Thank you. Hello, everyone. My name is Xin Li. I'm working in the operational modeling group at the German Federal Maritime and Hydrographic Agency. My post will show you some new implement in our operational model system. And at the BSH, we use HBM model for the forecast. And for the data simulation, we applied ensemble common filter in the PDEF. And now we have different modulars to simulate different observations. For example, we can simulate 2 different SST satellite products, and it's already run operationally every day on a daily basis. And we have new data simulation component to simulate the sea ice concentration and sea ice thickness. We plan to apply this new data simulation component for the winter season this years. Before we applied it, we have made different experiments. One experiment, we compare the data simulation with using different SST satellite products. And in the other experiment, we have compared the weakly and strongly coupled methods. And on my post, in my post, you can see some results, and it shows. But it shows using the different SST products leads to different results. And when we use CMEMS SST, we get positive increment. The sea surface temperature increased, and if we use the other product, maybe HRR SST, and then we get a negative increment. And this have a large influence, great influence on the ice formation. And yeah, and then we also compare the ice extent and ice concentration distributions. And yeah. And in the experiments about for the coupling methods, we have found that in the weakly coupled data simulation, we have erroneous increment on the SST, and through the strongly coupled, these errors can be corrected. So far for my poster, and if you have any questions and suggestions by my poster.
No. Okay, the last poster is Gao from NMBFC. Oh. Okay, I guess they're not here. Okay. All right. Let's see. So our next presenter is Yu Ying from NERSC, who will be talking about improving vortex position accuracy with a new multi-scale alignment ensemble filter.
Thank you very much. So in this talk, So in this talk, I want to share with you quite long experience so far. I've started doing this topic since my postdoc at NCAR with Jeff Anderson. So it's first of all, I need to say it's quite nice to be here to address this community, which focuses more on ocean. I understand, but yeah, it's nice to demonstrate maybe something what happens in the other like ensemble DA community too. So we at NERSC in Norway, we are working more on the Arctic, where the sea ice is very important. But when I started developing this method, it was more focusing on weather community, where hurricanes and fronts and just basically heavy precipitation. These features are constantly problematic in forecasts. A lot of problem comes from nonlinearity caused by position mismatch. So here's the motivation. First, I use this ranking vortex, which are shown in the contour lines here, to demonstrate how nonlinearity caused by position error will degrade ENKF results. So on the first row, the different colors means member having exact the same vortex, but just the location is slightly off. But if the location position error is not so big, then the distribution is quite normal. So in this assumption, the ensemble common filter should work optimally, where you see that the analysis behave very, very nicely. So when I start allowing the position error to increase into the second and third row, now you'll see that in the middle column that the ensemble common filter struggles to create a nice vortex structure in the analysis. This is because when you have features spread out in space and the value distribution, the sort of PDE in any spatial points is not guaranteed to be a Gaussian. So you see that the dotted line, the dotted red line are the Gaussian with the matching first two moments, but then the sample distribution basically deviates either with some skewness or with some kurtosis. Oops. So in data simulation, we try to model our error. So first, if the error is normal, we can just say the state is xb time equals to the x star, which is the truth, plus the one error. But that now with this nonlinear error, we separate the error into two terms. One is amplitude, one is phase. So basically, ED is the displacement error, which we can model by displacing the model grid. So we can kind of warp the coordinate system of the model. So xb Q here is some displacement vector pushing the grid box to the different spatial locations. So this kind of displacement error can be very nonlinear, even though the displacement vector itself is quite linear. ER here is the residual error. So if you do another subtraction of the truth, now you get some residual, which is the B matrix. It goes back to the Gaussian assumption again. But the problem is B here is now a function of the Q, which is the displacement vector. So in Bayesian formulation, we did a little bit of a chain rule here. So our posterior distribution will not only be defined on our state, so the image, but also it is defined on the displacement vectors. So that's something we want to solve together. So the cost function looks like this. The first two terms is very familiar to you. It's the observation mismatch and the state prior. And this state prior is just for the residual error, so ER here. And the third and the fourth terms are the further minimizing for the cost for the Q, so displacement vector. So this actually comes from the old idea called the feature alignment technique, FAT, which actually was implemented by Tom Nercombe in JEDI too. It also exists in the variational framework, but we are trying to solve this in the ensemble framework by solving this nonlinear cost function with two steps. First, fixing Q and Q equals 0, and then we minimize the cost function in the similar way to the ENKF. So we call this the ENKF update. And the second step is actually deriving what Q should be given the ENKF analysis. So the difficulty of solving the nonlinear cost function in one go is that the nonlinearity causes very high dimensional topography problem with this solver. So if you can imagine the J cost function defined on X and Q simultaneously is a very jumpy cost function. So if you want to do down gradient search, it's very easy to stuck in a global minimum, in a local minima. The idea we use this multi-scale loop is similar to the outer loop in 40 bar. So we smooth the state, constant resolution representation of the X here. Now the cost function is more smooth. So in a sense that we start from anywhere in the domain, we can find the near to the global minima quicker in this cost resolution outer loop, and then we can refine the resolution to search further into the minima. Yeah. Okay, so this is a graphical depiction of the idea. We do Hurricane Patricia, which is a vortex system. The three rows here show three different scale components. The first row is really large scale. So I'm showing the zonal velocity map here. You can see the vortex quite big. So from the prior to the analysis, I derived this incremental update with my enkf and solve for the vector field, which kind of explain how much of the vortex I need to push toward the center of the domain so that it matches the analysis. So these vectors, I assume that explain a lot of the positional mismatch of the vortex. So I can use this vector to align the whole thing, not just for the large scale. So I apply these vectors for the analysis large scale, also to the smaller and medium smaller scale. So you see that for the medium scale, from prior, before doing the enkf again, we actually pre-align the vortex with these vectors. So with the aligned prior, we do another enkf update to the analysis, and then we can start this process again, solving for another set of Q vectors and apply to the final small scale. So this iterative loop is very efficient in the sense that it helps precondition the small scale before enkf, making this enkf, although it's a linear optimal solution, but then if you apply it maybe in an iterative sense to solve the nonlinear problem, you need a lot of iteration. But in this scale loop, you reduce the number of iterations required. So this is the pseudo code for the whole thing. I want to highlight this the fourth line in the code, if decompose observation. So we started by in 2019 by introducing this method without decomposing the observation into different scales. So we have the full resolution observation in updating model states at different scales. But in recent paper we published, we include this observation decomposition option. We call it MSA-O here. So it also matches the observation with the model state. So we kind of do the spatial bandpass filtering for both state X and observation Y, so that when you do the enkf, the right-hand side, the update is really consistent. Yeah, it's hard to point to things, but let's highlight line 7 and 9. These are the enkf update equation. You can think about this like a 40 var without the time domain. So it's like running the nonlinear model for the tangent linear version. So in a mathematical sense, enkf is almost equivalent to 40 var. So line 12 here is the additional step we do for alignment. So we're solving for the Q vectors, and the first term in the minimization is the mismatch between XB, Q minus XA, which means given the analysis XA, how much if I move the prior image around, can I minimize this residual error? So that's how we solve for Q. And the regularization term on the second here, W times nabla Q squared. These are just penalizing the jumpiness in Q. So we don't like the displacement vector to be pixel by pixel very different. So it will kind of distort the image too much. So in a sense, we want smooth Q vectors, vector fields. Okay. So these are just ideas. Now I show you some stress testing with some simple model. The model I use is a two-dimensional vortex, the same kind of vortex I showed in the beginning. But to make the problem more challenging, I also included background flow. So it's not only the vortex, but also some background random velocity field. So the vortex, over time, it will move around and also experience some growth in the vorticity. So I show a typical power spectrum. It looks very much like the atmospheric power spectrum. It's a red noise spectrum. I divided this system into four scale components, S equals 1, 2, 3, 4, and the second row is the model state. So the vortex looks like this in the scale components. And the final row here is the observation. So if I have an irregular network, maybe the airplane flies into the hurricane and drops sounds to pick up the wind speed, and this will what it look like with these dots. I can do the same spatial bandpass filtering for the observation, and that looks like the bottom. A little tricky point of the observation is that you don't necessarily have enough information for the small scale, S equals 4 here. So if you do the same spatial filtering, you can see that doesn't pick up the nice structure in the panel G here, where the vortex has a very nice quadruple polar pattern, but in the actual observation component, it's no longer, it's just a very, very numerical random noise. So I want to test if I increase the number of scales, do I go to some nonlinear solution, optimal nonlinear solution? So I use the particle filter to pick the closer member to the observed value. So the observation here is the plus sign, and I can use particle filter to say which members in my ensemble match this observation better, and I basically assign these members better weights, and then kick out all the the members with low weights. So the particle filter is supposed to be a very good nonlinear solution here, and you see that from the prior to the particle filter, it's a very big difference. But if I increase the number of scales in my multi-scale alignment technique, I also approach that behavior. On the bottom here, I show some comparison. So without the data simulation, one of the member is biased toward the bottom right. With just the pure ENKF, so the square root variant, it's going to try to update this system linearly. So it will try to wipe out the old vortex and plant in the new vortex. But because you do this only linearly, it's going to end up have a kind of stretched shape, if it makes sense. So if I only do multi-scale ENKF, so I do the ENKF in the four different scales loop, it's going to solve a little bit of the problem by not updating too much the new vortex. So only if you do alignment in the final panel here, you can actually stretch the model grid so that the vortex gets moved to the new position. So the test also showed that it's quite robust. I did 2,000 random realization with the initial, so we assigned different seeds for the test. And the color box plot showed the distribution of the 2,000 realizations. The error statistics, I did it both for domain averaged error in the wind speed and also for position error for the vortex. So there are slight problem with the position spread equals 0.2 here. So the spread is 0.2, which means it's very, very linear. So it's like almost not too much spread, where the ENKF actually should perform very nicely. But my problem is that with the new method, I slightly degrade the result. Like you see the blue bars are actually larger than, higher than the white bar. So the problem here is because we are not moving around the vortex more than one pixel. So when I actually did my warping, I interpolate too much the new features into the old common reference grid. So by interpolating, you see this profile showing in blue here. So if you miss the peak of the wind speed in between grid cells, and if you do interpolation, then it's very diffusive. You don't have sharp gradients anymore in the system. So this is explaining why I have the degradation, but this is easily solvable by having either a higher resolution grid for analysis or just use Lagrangian approach. So if you move a little bit, then actually move the grid, don't do interpolation. So it's okay. And we also show that in the highly nonlinear regime, so position spread equals 1, we are rapidly approaching what the particle filter can achieve. Slight problem with the particle filter is that actually it gets a very large variance of the results. That I don't have time to explain that, but yeah. So how am I doing on time? Yes. So the challenge now is the relationship between large and small scale component. Remember that I made assumption saying the large scale position error, the displacement vectors, I assume that they exactly explain the small scale feature position error. So I will just apply it Q1, Q2, and Q all the way to QS-1. All these displacement vectors will be applied exactly to the S scale component, which is problematic if my background flow displacement is actually incoherent with the vortex displacement. For example, if you have a high pressure system where the high pressure needs to move to the south, but the hurricane actually moves to the west in prior members, and then they are not related to each other. If you solve for the high pressure system displacement error and say, okay, my hurricane needs to move to the south, then you increase the prior displacement error. So this is a problem. So I shouldn't always assume that Q and the residual errors in the small scales are fully correlated. So this is also showing that if I do the incoherent background flow, then my method no longer further improves the result. It sometimes even degrade result. So we are thinking now instead, maybe we can do some prior, maybe we can update the small scale Q with the prior knowledge, then because we have a relationship between the large and small scale determined by the ensemble, we can do this update better. If they are not really coherent, then we can just discard the large scale Q. Yeah. So, and the time is up. This is briefly showing performance in the cycling data simulation. We show that in the not only in analysis but also in forecast, the method are performing better than just pure ENCAF. One thing to point out maybe is the temporal growth of error. So if you see the error sawtooth graph, and the red one is having a lower slope than the black one, which means our improve the vortex position will not only be better result for the analysis, also the vortex error will grow slower in the future forecast. So to summarize, I'm working on this position error reduction. It's not only for toys, not only to play. I do see a lot of vortex in the fronts show up in the forecast being in the wrong location. This is a ubiquitous problem. So I've stress tested the MSA in the vortex case, and this is the reference, a recently published paper. Yeah, that means I need to stop. Thanks.
No, sort of. Yeah. Okay. Thank you very much. Yeah. Do we have any questions?
Thanks a lot, Yue. Do you have any plans to extend it to the 3D case, and do you see any major challenge for the 3D extension?
Extended to
3D-dimensional models.
We tested briefly with Hurricane Patricia, so it's a 3D system, and the assumption is that the Qs are identical for all the layers. If you relax that, maybe potentially you can shear the vortex too much. And there are examples for the variational version of this. They tested it in the local convective cell systems. So it's a precipitation clouds cluster, and it appears to be working too. It sometimes doesn't work because of the problem for the large and small scale relationship. I think it's quite tricky for the fluid system. And also sometimes you cannot tell exactly it's the instantaneous velocity or it's the integrated result, or that the features had the apparent motion. So if in the DA you have corrected for the apparent motion, maybe as an integrated result, then it's hard to translate that to the instantaneous wind field because they are not a one-to-one map. These are the big challenges.
I have a few questions, but I couldn't really understand the details of your method. So I'm going to ask you a few general questions, and maybe we can chat offline. So my first question is, what's the dimensionality of the Q? Is it the same dimension as the state vector?
Yeah.
And the second question that I have is, Do you assume that the observations are the same dimension as the state? Like, do you need a full field observation for this method to work? Thanks.
Yes, thanks for the question. So the dimension of the observation is similar to the ENCAF. It doesn't need to be as big as the state. So typically you have a much smaller dimension of the observation than the state. So my formulation of the problem will exactly solve for the Q where there are increments from the ENCAF. So if you don't have observation in some spatial position, there will not be any ENCAF increment. So by definition, there will be no Q there. So I allow this Q vector to be defined on independent, on individual model pixels. So each state will have a separate Q, and I only constrain that the neighboring Qs should not be vastly different. So it's a smoothness constraint. So you won't have any Q where there's no ENCAF update. But where there's ENCAF update, there will be some movement going on, and that movement bleeds into the zero, so the surrounding. So it's a blending basically.
Thank you. I have a clarification question.
Yeah.
When you go back to your cost function on one of the first slides.
Yeah.
So when I go from a Bayesian to the cost function, I understand the first term, the second term.
Yeah.
And maybe the last term, but where did the third term come from?
The third term is a result because of taking the derivative of the old P, so the posterior PDF, because B is a function of Q now. It's not a complex function, but now because it's a function, then it jumps out. It's almost like a constant term in this formula. When the Q is not changing, then you don't need to worry about this. So log of B of Q. So the only show up in this when you try to solve for Q, and Ravila 2007 also showed that it's basically the constant level. So when you have some Q, it changed the overall magnitude, but it's not so strongly dependent on the exact pattern of Q.
And why is it logarithm?
Logarithm is because the P here is exponential e to the negative j. So where you take the derivative, there's a log because of that constant term is inside the e, and then
Okay,
I need to
thank you.
go back and check, but yeah.
Thank you. Does the cost of the method go up with the number of scales that you
Cost?
Yes.
If I do the multi-grid approach, so the large scale is less number of grid points than the smaller scale. I can always constrain my additional cost to half of the original problem. But if you choose to run the full resolution all the time, so the number of scale is the multiplier. So if you do it 3 times, it's 3 times the original ENKF cost.
Okay.
Yeah.
Okay. Question?
I was wondering if does the method improve the magnitude of the center of the vortex as well as the location?
Yes. You can say that the feature you can either specify it, but in our formulation, it's found by the analysis increment. So you don't need to say which feature is of interest. Yeah. So, but when we do diagnostics, we for the position error, it is the center location XY coordinate that we are working with.
But does it improve the accuracy of the magnitude of the center?
Yes, in my paper, I show also intensity and the size. There are some little problem with the size because the algorithm I use to diagnose size cannot do too. It's not so sensitive about the shape. So there are some tricky technical detail in there, but I show that overall you improve both the feature and also structure.
Okay, thank you very much.
Yes.
We should move on now. Thank you. All right, the next speaker is Sébastien Barthélemy from the University of Bergen, formerly at Surfax. Bad. He's going to talk about hybrid covariance super resolution data simulation.
Yes, thank you. So yes, this talk today is about hybrid covariance super resolution data assimilation. And this is a joint work with Julien Brajard, Laurent Bertino, and François Cougnon from the Nansen Center in Bergen, Norway. And I am Sébastien Berthelemy from the University of Bergen. Okay, so I will start with a short introduction to show the objectives of this work. And yes, so first, the objectives are twofold. On one hand, this is to emulate a high-resolution ENKF by running the forecast step in a low resolution with a low-resolution model in order to reduce the computational cost of the NKF, and also to take advantage of high-resolution observations with a low-resolution model. Okay, so basically, let us imagine a low resolution ENKF. So we perform the data assimilation step in a low resolution. When an observation is available, we perform data assimilation, and then we get a new set of analyzed state that will be used as initial conditions for further forecast. So the advantages of this is that the computational cost is low, which allows for a large ensemble size. But the error to the true background error covariance matrix that we would get from an infinite ensemble can be large because the high resolution processes are poorly resolved. On the other hand, if we consider an NKF in a high resolution, this time the computational cost is large, which limits the ensemble size, but the error to the true covariance can be smaller than in the case of the low resolution. And so the idea is how to combine the benefits from the two ENKF at these two different resolutions. And one proposition of a solution is what we have called the super resolution data assimilation that we call SRDA. In this case, you perform the data assimilation step in low resolution. Before the data assimilation step, we perform this super resolution step that consists in downscaling the low resolution member to the high resolution space. We perform data assimilation in the high resolution space, and after the data assimilation step, the members are upscaled back to the low resolution grid. So the term super resolutions means simply that we increase the resolution of the members. In this case, the computational cost of the method is low, which allows, again, for a larger ensemble size. The high-resolution processes are emulated, and which allows to limit the error to the true covariance. So in this work, we have used the quasi-geostrophic model from the paper of Salkov and Oke 2008. So a different resolution that you can see on the right, the high and the low resolution. We have performed synthetic experiments where the observations are generated by adding Gaussian noise to a true run of the model. And the observation points are the black dots on the figure, and their distribution across the domain is supposed to mimic the satellite track. And also, in the case where we degrade to the low resolution model, we switch the observation point to the closest green points, which results in a representativeness error. And the question is, one question is, for the super resolution step, we have the choice between two downscaling operators. So the first one that a cubic spin interpolation operator that we will refer to as a cubic in the following, and also a neural network that we refer to as a NN, and that has the properties derived from the how we trained it to correct to some extent the low resolution model error. Okay, so first I will present the results that we got with the super resolution data assimilation. And basically, if we consider a synthetic experiments with 500 assimilation cycle and 25 members, we consider in the first time the CPU times of the methods. So on with the figure on the left, where you can see the computational time of the NKF in high and low resolution. So these are the blue and the red bars. And the SRDA cubic and neural network in green and left. So the first thing we can see is that the computational cost of the ENKF in high resolution is the largest of all the methods, while that of the ENKF in low resolution is the smallest. And in between, we have the computational cost of the SRDA, whether we consider a cubic or a neural network. And in particular, this is closer to the ENKF in a low resolution. Now, if we consider the mean RMSE over the 500 assimilation cycles minus spin-up period, we can see that the NKF in high resolution has the smallest RMSE, while the NKF in low resolution has the largest. And in between, we have the SRDA cubic and neural network. And in particular, in the case of the SRDA neural network in green, we have the RMSE that is close to that of the NKF in a high resolution. So the conclusion of this is that this SRDA neural network provides a good compromise between the RMSE on one hand and the computational cost on the other hand. Now, if we consider DA experiments with constant computational cost of integration, we consider the trade-off that we have between integrating high resolution members and low resolution members. And in this case, running one high resolution member is equivalent to running 8 low resolution members. And here again, we performed twin experiments with 500 assimilation cycles, and we compared the performance at equivalent computational cost of 5 to 15 high resolution members with a step of 2, and which results in the particular case of the SRDA to 40. So there is an error. This is 40, 56, up to 120 low resolution members. And of course, the localization and inflation are tuned to optimal performance. And what you can see here on this plot is the mean RMSE of the NKF in a high resolution and that of the SRDA neural network as a function of the computational resources that you can see on the x-axis and the mean RMSE on the y-axis. So what we can see is that for very limited computational resources, the SRDA neural network performs best at the ENKF and high resolution. But for higher computational resources, the performance of the SRDA neural network are limited by the error that arise from the emulator. And one question is, can we take the best of both worlds to improve further the results? And so this led us to what we call hybrid covariance super resolution data assimilation, that in short we call a hybrid SRDA. And this is just the natural extension of the previous method. In this case, so we have this schematic representation of the scheme. We have two different ensembles at two different resolutions, so high and low resolution. For the forecast step, we integrate forward in time both ensembles. Before the data assimilation step, the low resolution members are downscaled to the high resolution space through that super resolution step. We perform the data assimilation step in high resolution with an hybrid covariance, and right after the data assimilation step, the low resolution members are upscaled back to the low resolution space. In this case, so the high resolution processes are emulated for the low resolution and resolved for the high resolution. The computational cost is somehow customizable, and the ensemble size can be large. which results in error to the true covariance matrix that is also customizable. So as I said, in this case, we have an hybrid covariance. This is a linear combination between the covariance matrix computed from the high resolution ensemble and the covariance matrix computed from the low resolution ensemble downscaled to the high resolution grid. And this hybrid covariance matrix that we call pH is given by the expression 1, where alpha is between 0 and 1. In the case of where the downscaling method is the cubic spline interpolation method, so we call this case a hybrid SRDA cubic. This is strictly equivalent to the mixed resolution ensemble data assimilation method introduced by Rainwater and Hunt in their paper of 2013. And in the following, we compute the results over the high resolution ensemble. And in this case, the optimal alpha that we use for the hybrid covariance matrix is that such that the spread between the RMSE, such that we have a match between the spread of the high resolution ensemble and the RMSE. Okay, so here again, we consider twin experiments at constant computational cost of integration. So we still have this trade-off between high and low resolution members, and we perform twin experiments with 500 assimilation cycle with parameters tuned to optimal performance. And first, we will consider the case of the figure A, where we are limited to 10 high-resolution members. So it results for the SRDA neural network in 80 in an ensemble of 80 members because of this trade-off. And for the hybrid SRDA neural network, we have a sharing between high and low resolution members that starts from 2 high resolution members and 64 low resolution members, 356 up to 9 and 8 members. And what you can see on the figure A on the left is that in the case of the SRDA, hybrid SRDA neural network, we have a mean RMSE as a function of the sharing between high and low resolution that will always be lower than the NKF in high resolution. So this is the blue dashed line, and also lower than the RMSE of the SRDA neural network. So this is the green dashed line. And now, if we repeat these experiments, but for computational resources that range from 5 to 15 with a step of 2, we get this figure on the right that is just the extension of the figure I showed before to the case of the hybrid SRDA neural network in red and the hybrid SRDA cubic in black. And the numbers that you can see close to the point for the hybrid SRDA are the sharing for between high and low resolution members for which we have the optimal RMSE. And basically, what we can see is that whatever the computational resources available from between 5 and 15, the hybrid SRDA neural network outperforms the hybrid SRDA cubic, but also the NKF in high resolution in blue and the SRDA neural network in green. And we assume that there will be a convergence between the ENKF and the hybrid SRDA method between 15 to 20 members. Okay, so the conclusions of this work is that, as I said, the hybrid SRDA outperforms both the SRDA and the NKF, and also the mixed resolution ensemble data assimilation method for an equivalent computational cost of integration. The method is customizable and makes optimal use of the resources available. And also an important point is that the effort to implement the hybrid SRDA in an existing DS system is minimal. In the sense that we do not need to modify the existing models. And in the case of the hybrid SRDA, we just need to do a minor modification to the data assimilation code. So the perspective to this work is first to write a paper about, we have a paper that is in preparation. The SRDA only will be applied in the Topaz system. So this is the current work of Antoine Bernigaud at Nansen Center. And this is a work supervised by Julien Brajard and Laurent Bertineau. And in the case of the EU project Impetus for Change, I will apply this method in the Norwegian climate prediction model, NOR-CPM. Yep, so this is all. Thank you for your attention.
Any questions? Oh.
Actually, the ensemble sizes that you showed now for the high-res ENKF are very small, so up to like 15. So I wonder which variant of the ENKF are you actually using at ensemble size 15? At least per turb observation, ENKF should have enormous sampling error.
Sorry, I did not understand the second part of the question.
Okay, which variant of the ENKF do you use?
Which version of the we use the deterministic ensemble Kalman filter.
Okay, thanks.
Thanks, Sebastian. I have two questions. The first one is when you change the number of members, if I understood correctly, you leave the alpha parameter unchanged, but there should be some relation, intrinsic relation between the meaning of the weight and the number of members. So you also try to, because
yes, we always tune in these experiments. We always tune the alpha when we modify the sharing between high and low resolution. Yes, so the alpha is not always the same.
Okay, thanks. The second is when you mentioned to extend this to let's say a 3D model from the quasi-geostrophic for the neural network. Beside the size of the problem, you didn't find any issue, especially in terms of the destroying the cross-variable correlation, which in that case is a.
So in this case, the QG model that we have used was a 2D model. And so this question about destroying the cross covariance is a research question that hopefully we will address in the work of Antoine Bernigaud and when I will try to apply it to NOR-CPM. Yep.
Thanks.
So you said this was a 2D QG model, you said, right?
Yes.
But can you give us some sense of, because I know there was only a factor 2 difference between the high and the low resolution, and maybe it was a poorly chosen example at the beginning, but the solutions looked almost exactly the same. So how hard is this problem in terms of, you know, how much more is the high resolution model resolving than the low resolution model? Because the figure you showed at the beginning, they look the same.
Yes, so actually I did not show it here, but we have also an ultra low resolution model. So we have degraded by 4 times the resolution of the model. And we have kind of the same conclusions in the end. And in the case of the ultra low resolution model, the behavior of the two models is even more different than in the case of low and high resolution. So if you want, I can after I can show you some results we got with the ultra low.
Yeah, it's just because 2D QG doesn't do a whole lot when you change the. You've got to get a really, really, really high resolution to get it to do anything different.
Can you repeat? So actually, we realized that the downscaling method allows to some extent to correct the position of the eddies, for example. And so we assume that it does not modify much the mean of the ensemble. We do the validation in the high resolution. Mm-hmm. Okay. Mm.